Okay, thank you so much for coming back to this week's discussion. This week is week 3 for our Business 640 class, and what I'm going to talk about today will be Chapter 6 and Chapter 7. So let me share my screen. Okay, so we're in week 3, Process Improvement Week. So as we begin this week, you have this required readings to do. Make sure you read this while the government doesn't and can't manage resources like a private business. You will need that article to address a few questions that you're going to have to respond to this weekend. So make sure you read that article. We're going to talk about, again, Chapter 6 and Chapter 7. And this is your first week where you have an option of individual writing assignments. So you have 3 options. You can do it in week 3, 5, or 7. You only have to do one. So you pick which one you want to work with. But this is the first one that's coming if you choose to do that one. So with that, let me share this PowerPoint. Now, I'm not trying to teach via PowerPoint, but I thought it may be a more useful tool to possibly aid you in this week's discussion. So let's talk about Chapter 6. It's about looking at the process flow analysis, and these are some of the things that hopefully we will cover in this particular chapter. So process flow analysis is about viewing and analyzing that transformation process in a sequence of steps as the connected inputs to outputs, or in other words, a process flow. And it's used to discover what type of methods that could be better, or what type of procedures that could be enhanced as we deliver a product or service to our customers. And it's all about adding value for our customers, as you already know. And there's multiple ways in which we're going to measure the process flow, which is absolutely paramount to improving this transformation process. And hopefully we'll go over a few of those process measurements, such as processing time, throughput time, flow rate, inventory, and capacity. And hopefully we will also define bottlenecks and provide methods for calculating some of these measures. So this process thinking is the point that we look at work and how that work is being seen as a process. And it really begins in describing the process of interest as a system. And that system really does have boundaries. Boundaries, input, output, suppliers, customers, and systems flow. So a system then is a collection of those interrelated elements which in aggregate or in whole is greater than the sum of its parts. And I think our textbook on page 111 gives us a great example when it talks about the human body. But equally important, a business organization can also be viewed as a system. And you think about manufacturing, delivery, marketing, operating, finance, accounting, human resources, training, information systems, and you kind of see where that's going with a business organization that can also be viewed as a system as well. Every operation can be viewed as a system by identifying the transformation conversion system. And we kind of touched that on chapter 1. And this transformation system must be isolated from its environment by specifying what are the system boundaries. And they give us another example in our textbook where we talk about the case of a bank at the bottom of page 111, where they were installing a new information system. And part of that information system, they pulled together a cross-functional team consisting of different functions that's going to be impacted by that new information system and how those interactions came together in order to ensure that the system was working appropriately. Then over on page 112, when we talk about the process view of business, and that one of the most important contributions of this process thinking is that the business that is viewed as a system really has a collection of interconnected processes. And this is a process view of business. This is just that example of figure 6.1 at the bottom of page 112. When you're looking at this particular figure, think it from a viewpoint of a process view of a business where the process itself runs horizontal. The process itself runs horizontal, where the functional view is vertical. The different functions of the organization, marketing, operations, and finance, it is run in the vertical axis, where the process flow is run in the horizontal axis. So that's just a different view, figure 6.1. And as we view business as a collection of processes, we must emphasize the cross-functional nature of decision making and how strategically important that is. And this figure kind of illustrates those different functions when you make handoffs to one other functional group or one more step in the process. And you can look at that and kind of draw a conclusion that at times the number of handoffs, the number of people who have to be communicated with, in some cases can make the process inefficient, or it could in turn, depending on how lean it is, could make it more efficient. But in either case, there's going to be some time component that's going to be dealt with, and this time-consuming process certainly is going to have to be communicated and dealt with. So again, figure 6.1, the vertical axis is the functions and the horizontal axis is the process. And if you look over on page 113, where we talk about the operations leader, that's another good area that you want to read, because this gives you a great example of some testing and how that testing began when they first assembled a team of experts to map out the process. And when they mapped out the process, they were looking at exactly what they were doing, what were the major activities when it came to clinical drug tests. And then after they did the mapping, they were successful in uncovering bottlenecks or areas where it needed to be improved. So again, a good point to read. And one of the first steps associated with that is they mapped out that process and how they use the cross-functional team in order to do that. Then the next comment with this particular chapter begins on page 114, where we talk about process flow charting. And process flow charting really refers to the creation of a visual diagram to describe a transformation process. Now, flow charting certainly has many different vernaculars, one of those being process mapping, flow process charting. And if you're talking about strictly a service operation, in that context, it would be called service blueprinting. And when we get into chapter 7, we'll discuss more about value stream mapping, which is yet another specific approach to flow charting that's really got its roots in lean system and lean thinking, Six Sigma, those type things. We'll get into that when we get into chapter 7. And as you think about flow charting, I think it's figure 6.2 at the bottom of page 114 gives us a very good example of how the specific form of the flow chart is used, but it is most common in a systems flow chart that we see here in figure 6.2, which again is just a graphical example. And in figure 6.3 on page 116, we see that how that is related to a service, how we're helping a customer in the service context. So as we think about the service blueprint, which captured the perspective of different people, the customer, the sales associate, and the tailor, is generally known as a swim lane flow chart, which is sometimes called a deployment flow chart or a matrix flow chart. So really, whichever one is being used, it really does not matter that much, as it matters about creating a flow chart that individuals can easily understand, and that it provides some basic tenets to it. In fact, those tenets or principles beginning on the bottom of page 115 through 116 are good principles to follow when you're talking about or considering building a flow chart. Number one was to identify and select a relative transformation process to study. Number two was to identify an individual or team of individuals to be responsible for developing the flow chart and ideally for the subsequent analysis. And that really instills, hopefully, ownership so they get an opportunity to actually fix something that's wrong with the organization. What's going to be the boundaries and how those boundaries are going to be established, which is absolutely paramount in step number three. And step number four was to identify and sequence the operational steps or the activity necessary to complete the output to the customers. And step number five was to identify the performance metrics. And you always want to identify performance metrics from a business perspective. You always want to know that as you're deploying your resources, that those resources are being utilized to its maximum. Because if you're going to devote resources to do a value stream, in some cases that may be a little bit laborious, and it's going to take away from the day-to-day operation of the organization if they're dedicated to do that value stream. And you want to make sure that you're going to gain some tangible benefit from the investment that that company is going to make. So you want to make sure you do step number five and identify the performance metrics. And in step number six, you're actually going to draw the flow chart and define it, and you want to identify the type of symbols that you're going to use so that you can have consistency in that flow chart. And again, figure 6.3 on page 116, page 117 goes into some very good detail. And there it is, the process flow charting, which we just talked about on pages 115 and 116. Then, as we continue on at the bottom of page 117, you see figure 6.4, which is this figure here. This is some common flow charting symbols. And we can see that the process, the decision, the terminator, and the flow of work, all these symbols mean something, but equally important, what they indicate is how someone could build a flow chart, and that with these constant symbols, they're able to look at that flow chart and immediately understand what's going on with the flow chart. Like this eclipse, let's start with the top one. The square box, so to speak, is that process flow. It denotes an operational step or activity to be performed. The triangle is a decision point or an evaluation point, or if then condition, then this is what we're going to go do. So it's really a decision point. The ellipse or circle is a start or end point, and the flow directional arrow just means that it's the direction of the flow from one step to another. Then we have example, again, this is example 6.2 that we talked about on page 114, which we've already discussed. And then over on, as we're talking about symbols again, figure 6.5 on page 118, this is another example of a process flow chart that's using symbol keys so that it would identify exactly to the reader of that flow chart what all the symbols mean. Very similar to this concept here. This is a graphical representation of it, just another set of symbols. But whichever specific forms of flowcharts are being created, the individual or the team responsible may choose what symbols they want to use. And that's okay as long as a key is provided, those symbols are used consistently in that flowchart, and the reader can pick it up and easily identify what they are talking about. And in figure 6.6 on page 119, this is figure 6.5. In figure 6.6 on 119, you just see another example of flowchart. So you have multiple examples to kind of reinforce this concept. So let's talk about process flow analysis and asking questions. And as we indicated already, when you're doing a flow chart of a transformation process, you got to make sure that you understand what you're trying to solve or what is the real problem. And once you created the flow chart to help you identify what those parameters, those boundaries are, then you can analyze, hopefully, the insights into how that transformation process can be looked at, evaluated, and improved given a specific improvement goal or specific measurement. A systematic approach should be followed to analyze when you create a flow chart in this underlying transformation process. And this is epitomized by asking these questions in the tables 6.1 and 6.2 over on page 120. Really gets into the 5 whys of what, who, when, and then how. What, who, where, when, then how. So this table, as well as your next table, are good questions for looking at a process flow analysis and determining the type of questions, again, as a starting point, not all inclusive questions, but at least a framework or a starting point that an individual or a group of individuals could use as they're looking at making an improvement in some particular process. Now, for these 2 tables, great information that you could take, put in your management toolbox, and pull them out when you need them to help you. So this is very useful information to me, not just from a textbook perspective or from an academic perspective, but from a real world application. And I've had the opportunity in my working career to use some of these very same questions when we were looking at problems were in my former employer. But it is good information. Hopefully, again, you could take it and put it in your management toolbox to add some value as you continue in your career. So as we go about measuring some of this process flows over on page 121, 122, once that process flow is developed, the real aim of it is to improve a process, a transformation process that has something is wrong. You want to try to go figure it out and determine where the improvements need to be. So once a process flow chart is aimed at improving the transformation process has been created, some basic measures of transformation process must be described or developed. And they should be developed in such a way that they're going to yield some tangible insights into the structure and performance of that particular transformation process. Over on page 122, we get into this concept called Little's Law. Little's Law, which was named after an operations researcher. And it basically shows that the average number of items in the system is the product of the average arrival rate of the system and the average length of time that it stays in the system. Or in other words, this is the average time in the system, is the throughput time. And that time is from when the processing begins until the product or service is completely finished. And they give us an algebraic equation of I equals T times R, or I being the average things in the system or inventory, T as in tank, I is India, T as in tango, being the average throughput time, processing time, plus waiting time, and R or Romeo being the average flow rate in the process. Then they give us some good examples there at the bottom of page 122. The first example was pretty straightforward, where we're trying to solve for I or India when they give us the T Tango or Romeo units. But in the next example is where we do a little bit of algebraic manipulation, where we're trying to solve for T. So you can see that T equals I divided by R. So just some basic algebra manipulation. So in other words, if I know any two of the three components needed to solve this, I can certainly find the other one, to isolate the other one using algebra, which you should be very familiar with that. But two good examples. I would certainly be familiar with those examples. Over on page 123, when we go into the process measurements, we're looking into the capacity, supply, and the demand. And the capacity is the maximum rate or the maximum rate of output from a transformation process, or the maximum flow that's going to be sustained over a period of time. And they use an example of an airport security. But let me stop just for a moment here when we talk about this throughput time, the average waiting time plus the process time. If you've ever been to your local grocery store or your local convenience store and you had to wait in line, well, you were then in a queue, and that's basically what that is talking about. Over on page 123 again, that capacity in the queuing or waiting line especially deals with when you have random arrivals. And if you've ever gone to get your hair fixed or get a haircut, you walk into your barber shop and the chairs may be empty, or the chairs may be full. So you have the waiting time that you will wait until you get into the barber or hairdresser's chair, plus the time that they will need to actually do the haircut or fix the hair. And that is really what I'm talking about here as an example. So with random arrivals, it makes it a little bit more difficult in order to calculate some of this, but when it's pretty standard, it's not too difficult. So queuing or the waiting line theory is covered in another chapter, and we'll get into that. But as we go down page 123, we look at, in general, there are n number of resources that process through each transaction, and we see here that the capacity equals the minimum capacity of the resource, starting from 1 to some infinite number. So no matter how much capacity you have, it's going to be limited by the minimal number of that particular function or that particular example. Let me come back to the example that they use here in our textbook in the airport screening example, when we talk about the resources, which include the workers who check the passengers' ID and boarding pass, and the operators who run the X-ray equipment and the X-ray equipment itself. No matter how many people that they may have employed, if every baggage has to go through the X-ray, and then the X-ray technician may be the minimum capacity. If they could have a gazillion people standing outside wanting to get into the airport, but until they get their baggage through the X-ray machine. So that really becomes the minimum capacity of the resource. And that goes on further to say that capacity of the entire process cannot be larger than the capacity of the most constraining or the smallest capacity resource, which is given this term called bottleneck. So in our example, I could have 1,000 workers, and I only have 10 workers based on my X-ray machines and what they're doing. So even though I have 1,000 workers to process a gazillion people trying to go through my airport, my bottleneck in this example would be the number of people I have and the number of X-ray machines that I have. But that's just a very rudimentary example of this thing called bottleneck. And the flow through that bottleneck, when you think about the flow rate, you're looking at the minimum value, whether it's supply, demand, or capacity. And they give us a great example to at the bottom of page 123 to kind of run that home. So in this particular example, we assume this is a factory and they have a capacity of 200 units per day. The demand is 75 units per day and the supply is 100 units per day. Well, the flow rate would be 75 units per day because that's the minimum of the three variables, assuming that they can only produce what is demanded. So that flow rate minimum is the most limiting capacity through the flow process. So be familiar with and feel comfortable with understanding capacity, bottleneck, and flow rate. We talked about Little's Law already, and there's just another chart, another graph, another PowerPoint slide on that, and it also assumes a steady state condition. It does not take into consideration, again, those random arrivals, which random arrivals is absolutely hard to predict, as you can imagine. So here's a measuring process flow at PISA USA 123, 124, 125. Great example of this, kind of try to reinforce this particular concept. And as they map their process as well, and what is the throughput time, again, on page 124, 125. Let's talk about process redesign. Process redesign. Okay, so as you go through this, you can see that again, that's 124, 125, and the end conclusion of that particular example on those 2 pages. So now let's talk about process redesign. Process redesign usually starts with identifying critical processes which are required to meet the customer's needs, and this critical processes may cut across organizational boundaries. This is where pulling together a process or a cross-functional team will be paramount to help identify those changes, hopefully eliminate unnecessary steps, hopefully by looking at it and defining where waste occurs and eliminating those waste or getting rid of duplicating steps. And part of this process redesign, when you think about it, we use this term called business process re-engineering. Bravo, Papa, Romeo, business process re-engineering. It also has another label, extensive process redesign. And when you think about this, this is really looking at deploying flowcharts and how we can better improve the process. And they give us a good example of Credit Suzy on page 126, 127 to kind of help reinforce those concepts. And really, this is about how the accounts closing process was analyzed, and what they found out in that accounts closing process, that most requests for account closing could be handled in a standardized manner and therefore could be automated. And through automation, they were able to improve the overall process through that. When you think about process redesign, it really is a radical redesign when processes simply cannot be improved in small steps and require a complete redesign to improve them in a major way. And in improving this process to pursue a successful process redesign, at the bottom of page 127 and 128, there were 4 principles that were identified to help us determine how we can go about doing this radical redesign. Organize around outcomes, not tasks. Have the people who do the work process their own information. And I'm a firm believer that if you really want to improve your work processes, do not let it come from the ivory tower thinkers who are separated away from those or separated away from the process, but get those people who have their hands involved in each and every day, frontline workers, to give you a hand. Put the decision point where the work is performed and build control into the process, and to eliminate unnecessary steps in that process. And in some cases, in our workplaces, we all know we have built-in waste into what we do. There are things that we do that may be regulatory driven, that may be a governmental agency, it may be a process or a procedure that came from our senior management and we know is there, so we're not going to change it, because if we change it again, we'll be violating law or some edict provided to us by senior management. So when you have those things, even though they are required, is there a way to do them better? Not that you are going to eliminate that step, but is there a way in which I can do that step better? And that's all part of this process redesign when you take a look at that. So that concludes chapter 6. Let me move on to chapter 7. Please let me change the other slide here and go back to chapter 7. And now we get into thinking, lean thinking and lean systems. Hopefully this is what we will cover, some of these activities here. Excuse me, the objective of this particular chapter. But you think about the evolution of lean beginning on page 135. It really has its roots too in World War II, as we were looking at how we were going to mass produce everything that we needed in support of the effort during that particular time, and how the production of standardized discrete products in such high volumes really started this thing of repetitive manufacturing technologies, and that really became the norm. And that's really where we, the United States, when it got its manufacturing process really in gear in World War II, at that time was able to become the world leader in manufacturing. And then in 1960s, Toyota Manufacturing, this is in U.S. manufacturing companies, determined that it could not copy their system of mass production. So they realized the foundation of what they needed to do with this thing called Toyota Production System and our just-in-time inventory. And it's now you see that just-in-time inventory and this TPS, or Tango Papa Sierra Toyota Production System, really come into play in more and more organizations throughout the world. And it's really looking at, this is where this concept of lean manufacturing really came into play, and how we define lean as a systematic elimination of waste in all production processes by providing exactly what the customer needs and no more. It certainly is a customer focus, but equally important, a manufacturing focus, where we are looking at the concept, principles, techniques, and lean production that is often referred to as lean thinking. And some of these lean tenets over on page 137, the first tenet in lean thinking is to specify precisely what about a product or service creates value from the customer's perspective. Kind of sounds like one of the first steps in marketing as well, to determine how we're going to create value for the customer. One of the first things we have to know is what does the customer want? What does the customer need? Or what do we think the customer wants or needs, and how we can go about satisfying that need. Waste in lean thinking is another, is anything that does not contribute value to the product or service being produced or delivered to the customer. Rather than adding value, waste add cost. And I've already indicated earlier that in some of our manufacturing processes, in some of our businesses, there is built-in waste. It is, again, maybe a regulatory requirement, may be required by law, may be required by our senior management, or our processes, our procedures, may even be something that the customer absolutely demands that's got to be there. And that is planned waste. And the key there is not that you want to eliminate that, because you may be violating those other things we just discussed, but is there a way in which I can improve that particular step to minimize that waste? And the Japanese term for waste is muda, M-U-D-A, which is just a term that is used to identify waste. And you see some of those terms there in table 7.1. Good information as you're thinking about learning these concepts, the 7 forms of waste: overproduction, waiting time, unnecessary transportation, excess processing, too much inventory, unnecessary motion, defects. Just the tenets that were described in the 7 forms of waste. The second tenet in lean thinking is to identify, study, and improve the value stream of the process for each product or service. And the value stream identifies all the processing steps that is needed or undertaken to complete a product or delivery of something good, tangible to our customers. One technique of supporting this tenet is value stream mapping, where we actually will create a visual representation of a process flow or manufacturing process, much like flow charting. And you give us a great example on figure 7.1 on page 138 when we're talking about someone actually making a direct observation, or GEMBA, GEMBA, making a direct observation as their value map stream mapping that manufacturing process. In this example, we're looking into a healthcare system when someone checks in, what's the process they go through, how many steps are involved, what's the steps in the process they go through in the visit prep, when they visit the doctor, whether they have to do follow-up or go get medication. And you see the times and the wait times, the throughput times there at the bottom. So that's just a rudimentary description or graphical representation of a simple steps going through a healthcare value stream map. But you could expand this, but this is where developing that cross-functional team so that everyone understands how the values map or the flow chart needs to be done. Then we could make direct observations of that to identify those areas where redundancy may exist, where waste is being incurred, where there may be opportunity to improve that value stream process. Okay, step number 3, or tenet number 3 in lean thinking, is to ensure that the flow within a process is simple, smooth, and error-free, thereby avoiding waste. And to appreciate this, again, if we look at figure 7.2, you can see another classic example of simple, smooth, non-wasteful flow. And the idea of simple, smooth, and error-free flow means that production flows are simple and direct. They do not change from one production run or one customer to another. In other words, predictability, predictability, predictability. And in this lean manufacturing, both workers and suppliers are charged with the responsibility of producing quality parts just in time to support the next production process. Another tenet, or tenet number 4 in this lean thinking concept, is to produce only what is pulled by the customer, which is complying with the tenets replacing a push system, which is typically in a traditional mass production, but with the pull system of the lean. So what's the difference between the two? A push system aims to produce goods or ensure delivery of services well in advance of the demand, often according to a scheduled plan or created from potentially inaccurate forecasts. So a push system produces goods or ensure delivery of services well in advance. So you can see a push system has the potential to increase inventory, has that potential. Now the opposite of that is a pull system, which waits for the process customer to signal a need for good or services before producing to fulfill that need. This is a good example, or a classic example, of just-in-time inventory. So both of them have their place in our business environments today, and in some cases they may use a combination of them both, depending on the type of business that it's in. If it has a critical component that is absolutely needed for the overall production, waiting for and trying to predict when something is going to, say, fail, may cost you more money, and it may be a better approach to use a pull system to keep the manufacturing process downtime at a minimal level, to have that component in your warehouse, even though you're paying taxes and storage and insurance costs. But that is negated by the fact that if, say for instance, if my plant has to shut down and I have to wait for someone to make me a part in order to get my plant back up depending on what you're manufacturing. Having that part in the warehouse could be negligible in cost in the overall aggregate. So you may see a pull or push system, but a push system again, you're having that inventory already on the shelf ready to go well in advance. For a pull system as you're waiting, hopefully great communication, great forecasting in your demand for your parts or your services so that you can fulfill that order just in time. The fifth tenet in lean thinking is to strive for perfection, and perfection requires continuous improvement of all processes, and in some cases, radical design when necessary. And this definition of perfection is used here in an affordable good or service delivered rapidly and on time that meets the needs of the customer. Now, this has some downfalls, especially when the customer's needs change. When the customer's needs are changing, the definition of the value changes, so does the definition of what constitutes perfection. So perfection is really meeting the needs of the customer, the exact needs of the customer in an affordable way. But any organization, as part of continuous improvement, is an organization that's constantly looking inward to try to determine where are the areas that they need to improve, then put in those improvement changes to enhance their distinctive capabilities, as well as leading towards long-term profitability of the company. Okay, so one simple and relatively powerful technique for improving a production system process is the 5 Whys. 5 Why techniques, or the 5 S's, part of the lean thinking. And I think we have those terms that begins the 5 Whys we've already talked about, the 5 S's at the bottom of page 141, where we look at the table 7.2, when we have the Japanese terms in the English translations and what each one of those terms and translations mean. But it's really a technique that can be used for organizing a workspace hopefully to improve environmental safety, employee morale, process efficiency. It's really all about improving the workplace to improve worker efficiency, which is always a good thing, something we always want to be doing. Here's the 7 forms of waste I think we've already talked about. We talked about value streaming already in the term Gemba. Figure 7.2 we talked about as well. The 5 Why techniques we kind of talked about, and this is just an example of a dead battery to help us with the 5 Whys. And here's the 5 S techniques that again, that's at the bottom of page 141, table 7.2. And some of the elements of a lean system. All right, so let's talk about the top of page 142, stabilizing the master schedule. And one of the ways that we can do that through this lean tentative, simple, smooth, and airflow is to develop a master schedule that allocates, that levelizes our workload, or in other words, it stabilizes our master schedule. And it's generally not used in services because this concept is a little bit different when you talk about levelization of workers to the workload, but the concepts still apply. So the mastering schedule for products is to perform a uniform load or equal amount of work assigned to each machine or to each worker. So it's really about levelizing the workload throughout a production, throughout a day, or whatever time measurement that's being used. And matching the supply to demand is typically illustrated by using this thing called TACA time. And you see that in figure 7.3. Let me stop just for a moment.